look up at the night sky. Go on, just for a moment in your mind, picture it. A tapestry of diamond-like points against a velvet black. For almost all of human history, those points were just that, mysterious, divine, distant. But in the last, breathtakingly short sliver of our time on this planet, we've learned what they are. Suns, other suns. And with that revelation came a question so primal, so deeply woven into our consciousness, that it defines our entire species' quest for meaning. Are we alone? For decades, we've tried to answer that question by searching for a reflection. We assumed, quite naturally, that the universe must be filled with variations of the only system we knew, ours. A star, a few rocky worlds close in. Maybe one at just the right distance for water to pool and life to stir. And farther out, the silent, giant guardians of gas and ice. We built our search for life on this blueprint. We called it the habitable zone. We looked for Earth-sized planets. We got excited about sun-like stars. We were, in essence, searching for ourselves. But what if the blueprint is wrong? What if the reflection we've been searching for is a lie? What if, when we finally held up a mirror to the cosmos, our own solar system didn't appear? This isn't science fiction. This is the startling, unsettling, and electrifying frontier of modern astronomy. Fairly recently, we figured out that basically all stars have planetary systems. It's the rule, not the exception. The universe is teeming with worlds. But we also figured out something that sent a quiet shockwave through the scientific community. Our own solar system is quite weird. In fact, we've never seen another one like it. Not a single one. Let that sink in. In a catalog of thousands of confirmed planets around other stars, the specific architecture of our home, the one that gave rise to ooses conspicuously, profoundly absent. So we are faced with a cosmic fork in the road. And the path we take has implications that shake the very foundations of our existence. Either we are an extreme rarity, a 1 in billion fluke of cosmic construction, or we've been looking with the wrong eyes, and we're on the verge of a discovery that will shatter our current understanding. The answer is coming. A tidal wave of data is on the horizon, from a silent sentinel a million miles away called Gaia, and it's going to tell us, once and for all, just how special we are. I'm here to take you on the journey to that moment. This is a detective story on a galactic scale, and like any good mystery, we have to start with the crime scene, our own, seemingly ordinary backyard. For centuries, the principle of mediocrity, the Copernican principle, has been our guiding light in science. It's the idea that there's nothing special about our place in the universe. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. Every time we've assumed we were central, we've been wrong. So, it was a natural and frankly humbling extension to assume that our solar system was just average. A standard issue, stellar system. One among countless billions. This assumption was the engine behind the search for exoplanets. When we started looking, we were looking for us. We built our models of planet formation based on the one example we had. A great, swirling disk of gas and dust collapses. Close to the newborn star, it's too hot for E's and light gases to hang around. So you get small, rocky worlds: Mercury, Venus, Earth, Mars. Farther out, beyond the frost line, you can accumulate vast amounts of hydrogen and helium, snowballing into the gas and ice giants, Jupiter, Saturn, Uranus, Neptune. It was a beautiful, elegant, and seemingly universal model. It had to be universal. Why would the laws of physics work differently elsewhere? This is the story I learned. This is the story we all learned. It's clean. It's logical. It makes sense. And when the first exoplanets were discovered in the 1990s, the excitement was palpable. We were about to find our cosmic cousins. We were about to see that we were, after all, just a normal family in a normal neighborhood. But the universe, as it so often does, had a surprise in store. The first worlds we found weren't just different, they were bizarre. The very first exoplanets ever confirmed didn't orbit a star like our sun. They orbited a pulsar, the superdense, rapidly spinning corpse of a massive star that had died in a supernova. A star that had literally blown itself to bits. The idea that planets could not only survive such an apocalypse, but form in its aftermath was staggering. These weren't places for life as we know it. They were bathed in intense radiation, worlds forged in a cosmic hellfire. They were a warning sign. The universe, it seemed, was far more creative and far more violent than our simple model allowed. Then came the gold rush. With the radial velocity method, measuring the subtle wobble of a star as a planet tugs it back and forth, we started finding planets by the dozen. And what we found was a gallery of giants, hot Jupiters, enormous gas planets like our own Jupiter, but orbiting so close to their stars that their years are only a few Earth days long. Their surfaces would be scorched to thousands of degrees. Where did they form? How did they get there? Our solar system had no such world. This was not in the blueprint. I remember the growing sense of disorientation in the astronomical community. It was a feeling I shared, reading the papers as they came out. With every new discovery, our solar system looked less and less like the standard model and more like an outlier. We had no hot Jupiter. We had no planet orbiting closer to the sun than Mercury. Our inner solar system was a quiet, spacious place with 4 distinct, varied terrestrial worlds. Out there, it seemed, the inner regions of other systems were often dominated by a single, monstrous world that had either formed there or migrated in, vacuuming up all the building material. For a time, we consoled ourselves. We thought, well, our methods are biased. The Doppler method is best at finding big planets close to their stars. That's all we're seeing. The quieter, smaller planets, the Earths and the Venuses, they must be there. We just can't detect them yet. And then we built a machine that could dot. In 2009, NASA launched the Kepler Space Telescope. Its mission was deceptively simple: to stare, unblinkingly, at a single patch of sky containing about 150,000 stars, and measure their brightness with incredible precision. It was looking for the telltale, repeating dip in starlight that occurs when a planet passes in front of its star transit. This was the method we needed to find the small stuff. The Earth-sized stuff. Kepler was a roaring, unprecedented success. It didn't just find a few new planets. It revealed a cosmos overflowing with them. The number of known exoplanets exploded from a few hundred to thousands. We finally had our statistical sample. We could stop guessing and start making real comparisons. We could, for the first time, hold up a true mirror to our solar system, and the reflection that came back was alien. The most common type of planetary system Kepler found wasn't anything like ours. The universe, it seems, has a favorite architectural style, and it's called peas in a pod. In system after system, planets of the same system tend to be of very similar size to their neighbors. Think of the TRAPPIST-1, System 7, roughly Earth-sized planets orbiting a tiny red dwarf star. All in orbits smaller than Mercury's. They're like a string of cosmic pearls. Other systems are filled with planets, all in the super-Earth, or mini-Neptune category worlds between the size of Earth and Neptune, a class of planet that doesn't even exist in our solar system. What we don't tend to find is what we have here, a clear, clean separation, a set of small, rocky, diverse inner planets, and then, beyond a vast gulf of space, a separate set of giant, gaseous outer planets. That configuration, the one we call home, appears to be the exception. The cosmic rule seems to be uniformity, not diversity. Order, not the mixed-up chaos of our own system. This is the core of the mystery. This is the crack in the cosmic mirror. Why is our system so messy? Why did we end up with this particular arrangement of worlds when the rest of the galaxy seems to be following a different set of instructions? One of the most compelling hypotheses is as dramatic as it sounds: the grand tack. Imagine the early solar system, just a few million years old. The giant planets are forming. Jupiter, the first and largest, begins to migrate inward through the primordial disk of gas and dust. It's a bulldozer, plowing its way towards the sun. Its gravity scattering the planetesimals in the inner system, disrupting the formation of any larger worlds. It's on a path to become a hot Jupiter, which would have meant no Earth, no Mars, no us. But then Saturn forms. It, too, begins to migrate inward, and it catches up to Jupiter. Their gravities lock into a resonance. It's a gravitational tug-of-war that halts their inward death spiral and sends them back outwards, like a sailboat tacking against the wind. Jupiter tacks and moves back to the outer solar system, leaving behind a devastated inner system that has to slowly, painstakingly rebuild itself from the leftover rubble into the planets we know today. If this is true, our solar system's architecture is the result of a violent, chaotic, near-catastrophic event, a gravitational dance that almost ended in disaster, but instead cleared the stage for Earth to form. It's a thrilling story. But is it a common story? Or was our solar system's adolescence a uniquely turbulent one? Did a passing star's gravity trigger this migration? Was it just a random fluke? We don't know. And the reason we don't know brings us to the heart of the problem, the fundamental blind spot in our vision. The reason we can't find solar systems like our own is that we've been almost completely blind to the one type of planet that defines our system: the cold, long-period Jupiter. Think about Jupiter. It's the king of our solar system. It's more than twice the mass of all the other planets combined. Its gravitational influence is immense. It shepherds the asteroid belt. It can fling comets away from the inner solar system, acting as a shield, or sometimes sending them hurtling our way. Many scientists believe it played a crucial role in making Earth habitable by reducing the frequency of catastrophic impacts during the early bombardment phase. But from a planet hunter's perspective, Jupiter is a shy, slow-moving giant. It takes 12 long years to orbit the sun. That's its Achilles heel. Let's break down why our two most successful methods have failed to find many Jupiter twins. First, the transit method used by Kepler. To see a planet transit, its orbit must be perfectly aligned so it passes between its star and us. For a planet with a 12-year orbit, the chance of that alignment is small. But even if we get lucky and the alignment is perfect, Kepler only observed any given star for about 4 years. You might see one transit, maybe, if you're incredibly lucky, two. But you need at least 3 transits to confirm a pattern, to be sure that little dip in starlight is a planet and not a star spot or some other artifact. Kepler's mission was simply too short to ever hope to confirm an exojupiter. It was blind to the very worlds that might define a system as being like ours. Now, the radial velocity method. This one can find a Jupiter. By carefully measuring the star's spectrum, you can detect its subtle wobble, and you don't necessarily need to watch for a full 12-year orbit to infer a planet is there. You can see the star's velocity beginning to change in a predictable cycle. So why hasn't it found thousands of them? Because it's incredibly time-intensive and resource-intensive. Telescopes using this method can only track one star or a handful of stars at a time. They can't survey hundreds of thousands at once like Kepler could. It's a follow-up tool, a confirmation tool, not a wide-field survey tool. We've been using a microscope to search for a needle in a haystack, when what we need is a magnet. This is the frustrating, tantalizing position we've been in. We have a mountain of data telling us that small close-in planets are common. We have a growing list of hot Jupiters. We have entire systems of peas in a pod. But we have almost no data on the population of calm, distant, Jupiter-like worlds in Jupiter-like orbits around sun-like stars. We are missing the patriarchs of other solar families. And so, the central question, is our solar system rare, remains utterly unanswerable. We have been trying to take a census of families by only counting the children who live in the busy city center. We have no data on the quiet, influential parents living in the suburbs. Without that data, we can't know if our family structure is normal or not. But what if I told you we've already built the magnet? What if I told you that right now, as we speak, a spacecraft has already finished collecting the very data we need? That the answers are already recorded, locked in a digital vault, awaiting the command to be revealed. The mission is called Gaia, and it's about to change everything. We've spent decades searching for our reflection in the cosmos, only to find a gallery of strange and wonderful faces, but never our own. Our methods, for all their power, have had a fundamental, gaping blind spot, hiding the most defining feature of our home from our view. We've been like detectives trying to solve a mystery without being able to see the most important clue. But now we have a new witness, one with perfect memory and impeccable vision. The stage is set for the greatest discovery in the history of planetary science. So, if our own solar system is the blueprint we've been searching for, why does the universe seem to be building everything wrong? And is Gaia about to show us that the error wasn't in the universe's construction, but in our own vision? But we are a stubborn and ingenious species. When we can't see a thing directly, we learn to watch for its shadow. We learn to listen for its footsteps. We become ghost hunters. And in our quest, we developed two brilliant, indirect methods to catch these phantoms. They revolutionized our understanding of the cosmos and revealed a galaxy teeming with worlds. But I need you to understand something crucial, the key to this entire mystery. Both of these brilliant methods have a fatal built-in blind spot, and it's a blind spot that has, until now, completely distorted our view of what's out there. Let's start with the first great method, the one that started the gold rush, the radial velocity method, or the Doppler wobble. It's a technique of breathtaking subtlety. You see, the textbook line that planets orbit stars is a lie, or at least a simplification. The truth is, both the planet and the star orbit their mutual center of mass, the barycenter. Because the star is so much more massive, this barycenter is usually very close to the star's center, often buried deep within its fiery interior. But it is not the center. The star is not stationary. It is perpetually falling in a tiny, graceful circle around this point, tugged by the gravity of its unseen companion. This means the star is moving. And when a source of light moves, its light changes. If it's moving towards us, the light waves are compressed, shifting slightly towards the blue end of the spectrum. If it's moving away, the waves are stretched, shifting towards the red. This is the Doppler effect, the same phenomenon that makes a siren change pitch as it races past you. Now, the wobble of a star caused by a planet is tiny. For a Jupiter-sized planet tugging on a sun-like star, we're talking about a velocity change of about 12.5 meters per second, roughly the speed of a bicycle. For an Earth, a mere 9 centimeters per second, a slow walking pace. Detecting this requires not just a powerful telescope, but an incredibly stable and precise instrument called a spectrograph, which can split the star's light into a rainbow, so detailed we can see the individual chemical fingerprints, the absorption lines, and measure their exact position. I remember the awe I felt when I first saw the radial velocity curve for 51 Pegasi b, the first planet discovered around a sun-like star. It was a perfect, smooth, sinusoidal wave. The star was rhythmically dancing to the tune of an unseen giant. It was proof we could find them. Through the 90s and 2000s, instruments like the Hires spectrometer in Hawaii and the HARPS spectrograph in Chile became master ghost hunters, listening to the subtle harmonies and dissonances in the stellar symphony, pulling dozens, then hundreds of planets out of the noise. But this method has a type, a very strong preference. It's most sensitive to two things: massive planets, bigger tug equals bigger wobble, and planets in very tight, fast orbits, a short orbit, means you can see the whole wobble cycle quickly. The perfect candidate for the Doppler method is, you guessed it, a hot Jupiter, a massive world whipping around its star in a matter of days, giving a strong, frequent, and easily detectable signal. What it's not good at is finding the quiet, patient giants. A Jupiter twin, with its 12-year orbit, imposes a slow, grand, and far more subtle wobble on its star. To detect it, you need to monitor that star for years, even decades, dedicating precious telescope time to a single target in the hope that it might have a distant companion. It's a painstaking, inefficient way to take a census. The Doppler method gave us our first taste of other worlds, but it could only ever show us the low-hanging fruit, the giants dancing frantically in the inner system. It told us nothing about the quiet guardians that might be standing watch in the outer darkness. Just as the Doppler method was hitting its stride, a new tool came online that would change the game entirely. The transit method. Instead of listening for a wobble, this technique involved looking for a shadow. The concept is simple. If a planet's orbit is aligned edge-on from our viewpoint, it will periodically pass in front of its star, blocking a tiny fraction of the starlight. That's it. A miniature eclipse. For a Jupiter transiting a sun-like star, the dip might be about 1%. For an Earth, it's a vanishingly small 0.008%. Detecting that is like measuring the dimming of a car's headlight from 100 miles away because a gnat flew in front of it. But we built a machine that could. The Kepler Space Telescope. It wasn't a general-purpose telescope. It was a dedicated photometer, a light meter, with one job: to stare. And in its unwavering gaze, it saw these tiny, repeating shadows everywhere. This was the revolution. Kepler could monitor 150,000 stars simultaneously. It was a wide-net survey, a true census. It wasn't biased towards massive planets. It was biased towards any planet that transited, and it was exquisitely sensitive to small ones. This is how we found our first Earth-sized worlds, inhabitable zones. This is how we discovered the peas-in-a-pod systems. Kepler showed us that the galaxy is stuffed with super-Earths and mini-Neptunes, worlds that don't exist in our own solar system. It revealed the stunning commonness of certain architectural styles. But for all its power, the transit method has an even more profound weakness than the Doppler technique when it comes to solving our mystery. First, it requires a perfect alignment. Only a small fraction of planetary systems will be oriented so precisely that we see these transits. We're missing the vast majority of systems simply because they're tilted at the wrong angle. Second, and this is the fatal flaw for finding Jupiter twins, time. Think about it. To even confirm a planet via transit, you need to see at least 3 of these shadow passes. You need to witness the rhythm. 3 dips, regularly spaced. For a planet with a 12-year orbit, the time between transits is, well, 12 years. You'd need to stare at the same star for at least 24 years to get 3 transits. Kepler's primary mission lasted 4 years. It was fundamentally incapable of confirming the existence of a single, true Jupiter analog. It might have caught one lucky transit, a single, unexplained dip in the data, which could have been a planet, a star spot, or instrumental noise. Without a second or third transit, you can't know. You can't confirm the ghost was ever there. So, we have our 2 champion ghost hunting techniques. One listens for the footsteps and is great at hearing the frantic sprint of a nearby giant, but deaf to the slow, patient tread of a distant one. The other looks for shadows and is brilliant at spotting the small, frequent silhouettes close to the light, but it simply doesn't have the patience to wait for the long, slow shadow cast by a giant on a wide orbit. This is the distortion. This is the blind spot. Our view of the galactic population of planets is like a map of Earth drawn only by someone who has visited major capital cities. They can tell you all about the skyscrapers of New York, the temples of Bangkok, the boulevards of Paris, and from that, they might conclude that Earth is a planet of dense, bustling urban centers. They would have no concept of the Sahara Desert, the Amazon rainforest, the Siberian tundra, or the open Pacific Ocean. They would be missing the vast, quiet, defining spaces of the planet. Our exoplanet catalogs are filled with the cities, the hot Jupiters, and the peas in a pod. We have documented the cosmic metropolises in stunning detail. But we have almost no data on the rural systems. The systems with wide, spacious orbits. The systems, in other words, like our own. The absence of Jupiter twins in our data is a gaping hole. It's the ghost in the machine. We can infer they might be there, but we haven't seen them. We don't know if our Jupiter is a common kind of guardian or a rare one. We don't know if the grand tack is a routine part of planetary adolescence or a freak accident. We have built a catalog of thousands of new worlds, a cosmic menagerie of staggering diversity. But the pattern that emerged wasn't one of diversity. It was one of uniformity, a strange, repeating order that made our own solar system look not just different, but chaotic, almost messy. The universe, it seems, has a favorite, simple way of building planets. And our home, with its mixed bag of worlds, its clear separation of rock and gas, its solitary giant standing guard in the outer darkness, violates that rule. We are the exception. We are the cosmic nonconformists. Let's look at the data. Let's look at what Kepler actually found. The most striking and most common architectural pattern we see is now known as the peas in a pod configuration. In system after system after system, the planets tend to be of very similar size to their immediate neighbors. The poster child for this is the TRAPPIST-1 system. 7 worlds, all roughly the mass of Earth, all orbiting a tiny, cool red dwarf star in a dance so compact that the entire system would fit inside the orbit of Mercury in our own solar system. They are a perfectly matched set, a string of celestial pearls. But it's not just red dwarf systems. Around sun-like stars, we find systems dominated by planets, all in the super-Earth or mini-Neptune category worlds between 1.5 and 4 times the diameter of Earth. These are the most common type of planet in our galaxy, and yet we have nothing like them here. In these systems, you might have 3, 4, or even 5 planets, all within that same size range, all orbiting in a relatively tight, orderly chain. Now compare that to our solar system. Look at the inner system alone. We have tiny Mercury, then Venus and Earth, which are twins, then a much smaller Mars. There's no clean progression. It's a hodgepodge. And then, beyond the asteroid belt, the scale changes entirely. Jupiter is over 11 times the diameter of Earth. Saturn is not far behind. We have a clear, dramatic discontinuity, a radius gap, not just between individual planets, but between 2 entire classes of planets. This clear separation of small, rocky terrestrials and giant gaseous Jovians, based on the Kepler data, it's rare. It might be vanishingly rare. The universe, it seems, prefers to build systems where the planets are peas in a pod, ordered, uniform, predictable. Our system, with its stark contrasts and its mixed-up architecture, is the outlier. The cosmic rule appears to be similarity, not diversity. So the question screams at us, why? Why is our system so different? If the peas in a pod model is the standard outcome of planet formation, what catastrophic event scrambled the eggs in our particular stellar nursery? This is where we turn to one of the most compelling and dramatic stories in modern planetary science, the grand tack hypothesis. It's a tale of cosmic violence, a gravitational drama that nearly doomed our solar system before it even properly formed. Let me set the stage. 4.5 billion years ago, our sun was young, surrounded by a swirling disk of gas and dust. In the cool regions beyond the frost line, Jupiter forms first. It's a hungry giant, and as it plows through the disk, it interacts with the gas and dust, losing orbital energy. This causes it to migrate, and it migrates inward. Think about that. The king of the planets, the guardian of the outer system, was once on a collision course with the sun. This inward migration is a disaster for the inner solar system. Jupiter is a gravitational bulldozer. As it moves sunward, its immense gravity kicks and scatters the planetesimals, the building blocks of planets that were forming in the inner region. It wreaks havoc. It likely destroyed the first generation of inner planets, preventing the formation of the peas in a pod, the super-Earths that are so common everywhere else. The inner solar system becomes a depleted wasteland. Our solar system was on a fast track to becoming just another boring, uniform system, or worse, a system with a hot Jupiter. But then a savior arrives, Saturn. It forms later, and it too begins to migrate inward. But because it's smaller, it migrates faster. It catches up to Jupiter. When it does, their gravitational fields lock into a powerful resonance, a specific orbital rhythm. This resonance changes everything. It's like two dancers linking arms and changing their motion. The combined gravitational pull of the two giants opens a gap in the protoplanetary disk and reverses their migration. They tack like a sailboat, changing direction against the wind. Jupiter and Saturn turn around. They begin to migrate outward, back towards the outer solar system, leaving the devastated inner system behind, and in their wake, from the scattered, depleted remnants of Jupiter's rampage, the inner planets had to pull themselves together. This is why our inner solar system is a hodgepodge. This is why Mars is so small, the building material was gone. This is why we have no super-Earths. The Grand Tack was a galactic-scale reset button. It cleared the slate and forced a second, more fragile, and far more diverse construction project. It created the conditions for a small, water-rich world like Earth to form. So, let's absorb the weight of this. The Grand Tack is a brilliant, plausible explanation for why we are different. But it raises a terrifyingly profound question. Was this event, this gravitational dance between Jupiter and Saturn, a common part of planetary adolescence? Or was it a freak accident, a 1 in a billion fluke caused by a passing star's gravity, or a particularly dense patch in the protoplanetary disk? If it's common, then solar systems like ours should be everywhere. The peas in a pod systems would be the ones that didn't have a Jupiter to mix everything up. But if it's rare, then our very existence hinges on a cosmic catastrophe. Think about what Jupiter did. It's been called a shield, deflecting comets that might have sterilized the young Earth. But according to the Grand Tack, its role was far more fundamental. It didn't just protect the cradle of life, it built the cradle. By destroying the first generation of planets, it created the empty, peaceful orbital space where a small, rocky world with the right ingredients for life could slowly and safely assemble. Our system's weirdness, its lack of uniformity, its very mesinses, might not be a bug. It might be the feature, the essential and terrifyingly rare feature that allows for a planet like Earth to exist. The evidence from Kepler is mounting that we are the cosmic outliers. The peas in a pod pattern is the rule. Our system, shaped by violence and chaos, is the exception. But here is the heart of the mystery, the silence that echoes through all our data. We haven't found them. We haven't found the other Jupiters. In our vast and growing catalog of exoplanets, filled with thousands of bizarre and wonderful worlds, the one type of planet that defines our own home, the very template for a life-friendly system, is the one that is conspicuously, almost suspiciously, absent. It is the ghost in the cosmic machine, and its absence forces us to confront a terrifying possibility. What if the cosmic guardian is a myth? What if, in the grand scheme of the galaxy, a planet like Jupiter is the rarest world of all? To understand why this missing giant is such a problem, we need to appreciate its resume. Why do we care so much about Jupiter? It's more than just the king of the planets. Many scientists argue it's the reason the king of the planets, that's us, exists at all. First, as we saw with the Grand Tack, it's the architect. Its migration and retreat cleared the inner system, dictated the small size of Mars, and allowed Earth to form from the leftover rubble. Without that event, we might be orbiting a super-Earth, a world so massive its thick atmosphere would crush any chance of life as we know it. Second, it's the shield. For decades we've had this picture of Jupiter as a cosmic vacuum cleaner, using its immense gravity to suck in comets and asteroids that would otherwise threaten Earth. The reality is a bit more nuanced. Its gravity can giveth as well as taketh away, sometimes flinging objects from the Kuiper belt inward. But overall, its presence does stabilize the inner solar system. It acts as a gravitational anchor, shepherding the asteroid belt and imposing a rough order on the chaotic dance of small bodies. It reduces the frequency of truly civilization-ending impacts over astronomical timescales. But its role might be even more profound. By delivering water-rich comets to the inner solar system during the late heavy bombardment, it could have been the provider, filling our oceans. Jupiter is not just a bouncer at the door. It might have been the bartender who served the drinks that made life possible. So, if a Jupiter is so important, shouldn't the galaxy be filled with them? Shouldn't our primary method for finding life be simply find a Jupiter, then look for an Earth in its shadow? This is where we run into the cold, hard limitations of our ghost hunting tools. Let's be perfectly clear. Finding a true Jupiter twin is one of the hardest tasks in all of astronomy. Let's break down exactly why. First, the transit method. Imagine we got lucky. Imagine a star 100 light-years away has a planetary system perfectly idjon to us, with a Jupiter twin in a 12-year orbit. For Kepler to confirm it, it needed to see 3 transits. The first transit happens, then we wait 12 long years for the second one, 24 years for the third. Kepler's primary mission lasted 4 years. It was mathematically incapable of ever confirming a single Jupiter analog. It might have seen a single, unexplained, dip, a tantalizing clue, but without a second or third data point, it remains just a ghost story, a maybe. Now, the radial velocity method. This one can, in theory, find a Jupiter. It doesn't need a perfect alignment, and you don't have to wait for a full orbit to see the star beginning its long, slow wobble. So why has it only found a handful? Because it's a terribly inefficient way to conduct a census. Think of it like this. The Doppler method is a sniper rifle. It's incredibly precise, but it can only aim at one target at a time. To find a Jupiter, you have to point this sniper rifle at a single star, and you have to keep it pointed there, taking measurements for years. You are dedicating one of the most powerful telescopes on Earth to a single star for a decade or more on a gamble. Meanwhile, a mission like Kepler was a shotgun blast, monitoring 150,000 stars at once. The Doppler method has been our tool for confirmation, not for discovery, when it comes to these long-period worlds. We simply haven't had the resources to survey the thousands of sun-like stars needed to find a population of Jupiter-twins. The result: a devastating selection bias. Our two most productive planet-finding methods are systematically blind to the very world we're most interested in. We have been brilliantly equipped to find the strange and the exotic, the hot Jupiters, the super-Earths, the peas in a pod, but we have been almost completely unequipped to find the familiar. We have been searching for a ghost, with tools designed to catch only the living. So, the silence is deafening. We have not found other Jupiters, not necessarily because they aren't there, but because we haven't been able to look for them properly. But this lack of data creates a vacuum, and in that vacuum, fear grows. The absence of evidence is starting to feel, to some, like evidence of absence. What if the grand tack is a freak event? What if the specific conditions that led to Jupiter's formation, its migration, and its timely rescue by Saturn are so uniquely improbable that they have hardly ever happened before in the Milky Way? What if most planetary systems form in the calm, orderly peas in a pod fashion, and never experience the violent restructuring that creates a mixed system like ours? If that is true, then the implications are staggering. It would mean that Earth-like planets in the habitable zone might be common, but Earth-like planets in a system architecture like ours are not. It means that most habitable zone worlds might be super-Earths, with crushing gravity and thick, hydrogen-rich atmospheres. Or they might be part of a tight-packed system like TRAPPIST-1, where the planets are so close they gravitationally jostle each other, potentially triggering constant geological upheaval and sterilizing. VOLCANISM. Our solitude would then extend beyond biology to the very foundation of our world. We wouldn't just be alone as a thinking species, we would be alone in the very structure of our home. The quiet, stable, spacious solar system that allowed life to develop and evolve over billions of years would be a cosmic anomaly. The giant in our outer system, which may have been essential for it all, would be a rarity. We know Jupiter was likely a guardian for life on Earth. We suspect it was the architect of our very existence. But what if we could step back from the keyhole? What if we could throw open the doors and see the entire stage? What if, instead of just listening for the footsteps or watching for the shadow, we could see the star itself dancing a silent, graceful waltz through the void? There is a way. It's an ancient technique, one of the oldest in astronomy, but it required a level of precision that was, for centuries, nothing but a dream. It's called and it's the key that will finally unlock the secret of the missing giants. Let's go back to first principles. Remember the barycenter, the mutual center of mass that both the star and the planet orbit. The Doppler method detects the star's motion toward and away from us along that orbital path. Astrometry does something different. It detects the star's motions side to side across our field of view as the star orbits the barycenter. It doesn't just move radially. It traces a tiny circle or an ellipse on the plane of the sky. From our vantage point, it appears to wobble back and forth against the backdrop of infinitely more distant and essentially fixed stars. This is not a new idea. This is exactly how Friedrich Bessel, in 1844, deduced that Sirius, the brightest star in our sky, had an invisible, massive companion. He painstakingly measured its position for years and saw this tiny, telltale dance. That companion, Sirius B, turned out to be a white dwarf, the first ever discovered. Astrometry has been used for centuries to find binary stars, to measure the distances to stars through parallax, and to uncover the dark companions of bright objects. But detecting a planet this way, that's a different league of difficulty entirely. The wobble caused by a Jupiter twin is almost impossibly small. For a star like our Sun, at a distance of 100 light-years, the wobble induced by Jupiter is an angular shift of about 50 micro-arcs/econds. To put that in perspective, 1 microsecond is the size of a period in this sentence, as seen from the orbit of Pluto. It is the width of a human hair, as seen from a distance of 500 kilometers. It is, for all intents and purposes, nothing. Measuring it from the turbulent surface of Earth, looking through our shimmering, distorting atmosphere, was considered impossible. We needed to get above it all. We needed a machine built for one thing and one thing only, the most perfect map ever made. So why go to all this trouble? Because astrometry fixes the fatal blind spot of the other methods. In fact, it turns their weakness into its greatest strength. Let's look at the math. The size of a star's astrometric wobble is proportional to two things: the mass of the planet and the distance of the planet from the star. Think about that. The farther a planet is from its star, the larger the star's wobble appears on the sky. This is the complete opposite of the Doppler method, which is most sensitive to close-in planets that give a fast, strong tug. Astrometry is inherently biased towards the planets we've been missing, the long-period cold Jupiters and Saturn. It is custom-built to find them. Second, alignment. The transit method is brutally picky. It only works for the tiny fraction of systems with perfect edge-on alignment. The Doppler method is also biased. It's completely insensitive to a system that is perfectly face-on to us, where the star's motion is entirely side to side, with no component towards or away. Astrometry, however, doesn't care. It can detect a planet's influence, regardless of the system's inclination. It sees the full two-dimensional dance. And third, we don't have to wait for a full orbit. With the transit method, you're blind until you see that third dip, which for a Jupiter means a 24-year wait. With astrometry, you are literally watching the star's path curve through space. After just a fraction of its orbit, you can see the arc, you can fit a model to it, and you can predict the rest. You can find the ghost by tracing the path it's pulling its star along, long before it completes a full cycle. The theory is perfect. The method is sound. It is, without a doubt, the ideal tool for completing the census of planetary systems. It's the tool that can finally find the Jupiters. But there's a reason we haven't found thousands of planets this way already. The reason is precision. I told you the number, 50 microseconds for a Jupiter twin. From the ground, even with the most advanced telescopes, the best astrometric precision we can achieve is around 500 microseconds, limited by the churning of our atmosphere. We're off by a factor of 10. We're trying to read the fine print on a coin from a mile away, through a heat haze. For decades, this was the dream that couldn't be realized. We knew how to do it. We just didn't have the eyes. We needed to build a telescope that could not just see the stars, but could pinpoint them with godlike accuracy. A telescope that could, night after night, year after year, measure the positions of 1 billion stars, and notice if a single one of them deviated from its predicted path by the width of a coin on the moon. It would need to be in space, beyond the atmosphere. It would need to be mechanically It would need to be a monument to human engineering. We built it. Its name is Gaia, launched by the European Space Agency in 2013. Its primary mission was to create a three-dimensional map of our galaxy. But to do that, to measure the parallax of 1 billion stars, it had to become the most precise astrometry machine ever conceived by humanity. Its precision, between 20 and 30 microseconds, better than we even needed. Gaia doesn't take pictures in a conventional sense. It has 2 telescopes at a fixed angle on a slowly spinning platform. It detects stars as they cross its field of view, and by precisely timing their passage, it can triangulate their position with staggering accuracy. It is, in essence, the universe's most perfect surveyor's tool. But in its quest to build this map, Gaia had to do one thing above all else. It had to measure the positions of stars with an accuracy that was previously the stuff of science fiction. And in doing so, it began to record something else, something we had been waiting for. It began to see the silent, gravitational dance of the stars. It began to see the wobble caused by the ghosts we've been searching for. The data was collected in silence, transmitted to Earth, and processed by armies of computers. And then, in 2023, it gave us our first tantalizing glimpse. It showed us that it could see the giants. To understand why Gaia is different, you have to understand how it works. This isn't a telescope that points at interesting objects. It's a scanner. It spins slowly, completing a full rotation every 6 hours. It's 2 telescopes scanning great circles across the sky. As a star drifts into its field of view, it doesn't just take a picture. It's tracked by a 1 billion pixel camera, and its light is broken down by a spectrograph. The key is time. Gaia converts the problem of measuring an impossibly small angle into the problem of measuring an incredibly precise time. It knows its own orientation in space with phenomenal accuracy. By recording the exact nanosecond a star's image crosses a particular point on its detector, it can triangulate that star's position relative to all the others. Over time, by combining 70, 100, 150 observations of the same star, it can average out the noise and achieve a staggering precision. The numbers still beggar belief. Gaia can measure a star's position to within 20 microseconds. Let me give you that image again. That is the size of a euro coin on the surface of the moon, as seen from Earth. It is the width of a human hair from 1,000 kilometers away. This is the level of precision we are dealing with. This is the machine we built to find the wobble. The first data releases from Gaia were about the stars themselves, their positions, distances, and proper motions. They revolutionized astronomy all on their own. But everyone was waiting for Drive 3, the data release in 2023. This was the one where the veil would begin to lift on the exoplanet data. And there, buried in the petabytes of information, they found them. The first confirmed planets discovered by Gaia through astrometry alone, designated Gaia 4b and Gaia 5b. Let me be clear, these are not the Jupiter twins we've been searching for. They are something else, something arguably just as fascinating. Gaia 4b is a monster, a super Jupiter, 12 times the mass of our own. Orbiting a star smaller and less massive than the Sun, Gaia 5b is even more immense, 21 times Jupiter's mass, skating the very boundary between a planet and a brown dwarf, another small star as its host. Increased volume, a larger wobble, is easier to detect from farther away. These long-period planets induce the largest physical wobbles in their stars. The larger the wobble, the greater the distance at which Gaia can detect it. This means the mission will be sensitive to these giants across a much larger volume of space, encompassing millions more stars. Dr. 5 won't just be a list of planets. It will be a demographic atlas of the outer regions of planetary systems throughout our galactic neighborhood. We will see the full diversity of giant planet systems, single Jupiters, multi-giant systems like our own with Jupiter and Saturn, and bizarre configurations we haven't even dreamed of. This brings us to the ultimate goal, the Holy Grail. Will we find a true solar system analog? A system with an Earth-sized planet in the habitable zone and a Jupiter-like planet in a wide, stable orbit. Gaia, on its own, has a limitation. Its astrometry is not sensitive enough to detect the wobble induced by a tiny Earth-mass planet. The wobble is just too small. It will find the Jupiters, but it will not find the Earths. But that's okay, because we have another tool, TESS, the Transiting Exoplanet Survey Satellite. TESS is Kepler's successor, and it is conducting an all-sky survey to find transiting planets around the brightest stars. And here's the beautiful part, Gaia and TESS are looking at the same stars. This is the powerful synergy that will finally answer our question. Imagine this scenario, which will play out thousands of times after Drive 4 and DR5. Gaia identifies a sun-like star that is wobbling. The wobble is consistent with a Jupiter-mass planet in a 5 astronomical units orbit. Candidate G12345J. Astronomers cross-reference this with TESS data for the same star. The TESS data shows a series of tiny, repeating dips in brightness. The period of the dips indicates a planet with a 300-day orbit. The depth of the dips indicates a planet with the radius of Earth. Candidate T-12345-E. Follow-up. Observations with the next generation of giant ground-based telescopes like the Extremely Large Telescope and space telescopes like the James Webb Space Telescope then study the atmosphere of T-12345e, looking for signs of water vapor, oxygen, methane, biomarkers of life. This is the recipe. This is how we will find Earth 2.0, not just as a lonely rock, but as part of a familiar family, a family with a giant guardian in the outer system. And if we find even a handful of such systems, it would suggest that the grand tack, or something like it, is a common part of planetary system evolution. It would mean that the architecture of our solar system is a reliable, repeatable blueprint for creating habitable worlds. The implications for the prevalence of life in the universe would be profound. The galaxy could be teeming with pale blue dots nestled in protective systems, just like our own. But we must also prepare for the other result, the null result. What if DR4 and DR5 come and go, and amidst the 120,000 new planets, we find only a handful of true Jupiter twins around sun-like stars? What if the combination of an Earth-sized world in the habitable zone and a Jupiter in a stable outer orbit turns out to be extraordinarily rare? This would be a different kind of revolution, but a revolution nonetheless. It would confirm the growing suspicion from the Kepler data that our solar system is a genuine oddity. It would mean that the violent, chaotic series of events that shaped our system, the grand tack, the late heavy bombardment, the specific arrangement of giants, was a cosmic fluke. If this is the case, then our solitude extends far beyond biology. We would be alone in the very architecture of our home. The conditions that allowed for a stable, billion-year chemical experiment we call life would be a statistical anomaly in a galaxy dominated by peas in a pod systems and hot Jupiters. Most habitable zone worlds might be turbulent super-Earths or tidally locked planets around red dwarfs. Environments far less conducive to the rise of complex, technological life. This would not be a cause for despair, but for a profound revaluation of our place in the cosmos. It would mean that this world, this beautiful, fragile, diverse planetary system, is more precious than we ever imagined. We are not just a common outcome of universal processes. We are a masterpiece of rare and fortunate circumstances right now. In astronomy departments, from Cambridge to Caltech, from Tokyo to Santiago, the anticipation is a physical presence. Graduate students are writing code in anticipation, creating tools to sift through the coming data deluge. Postdocs are running their own simulations, hoping to be the first to spot a pattern. Professors who have spent their entire careers studying a few dozen exoplanets know that their field is about to be turned upside down. This is not a passive wait. It is an active, frenetic preparation. They are preparing for the day the universe changes, because that is what will happen. Our philosophical and scientific understanding of our place in the cosmos is currently based on a skewed, incomplete dataset. We have been trying to understand the population of a country by only surveying its capital city, Gaia. Drive 4 and Drive 5 will be the first full national census. It will show us the sprawling countryside, the quiet towns, the vast, open spaces. It will show us the true demographic makeup of our galactic neighborhood. The data is not speculative. It is not a prediction of what might be out there. It is a record of what is out there, already observed, already measured. The wobbles have been recorded. The dances have been captured. The giants are already found. We are just waiting for the curtain to be lifted. We are on the verge of knowing, not guessing. We are about to transition from asking, "Are we alone?" to beginning to understand the context of our existence. We will know if we live in a common or a rare solar system. We will know if the universe is likely filled with life, or if we are a singular, miraculous accident. The answer is in the vault. The key is being forged. The clock is ticking down to December 2026. The data is coming. The final, definitive census of the galactic neighborhood is being prepared for release. Soon, we will no longer have to wonder if our solar system is common or rare. We will have the numbers. We will have the statistics. This knowledge will forever sever us from the innocence of our past. It will force a reckoning, a final, definitive answer to the oldest and most profound question we have ever asked. What is our place in the cosmos? Are we a common story, told on countless worlds, or are we the entire, singular, breathtakingly rare library? The revelations from Gaia's data releases will essentially present us with one of two possible futures for humanity's cosmic self-image. There is no middle ground. The numbers will point decisively in one direction or the other in this future. The data reveals that solar systems like ours are common, that Jupiter twins orbiting sun-like stars are found in 1 in 5 or 1 in 10 systems, that the combination of an inner rocky world in the habitable zone and an outer giant is a standard, repeatable outcome of planet formation. This would be the ultimate validation of the Copernican principle. We are not the center of the universe, and our home is not a special design. It is a common blueprint, the violent history we infer for our own system, the grand tack. The late heavy bombardment would be seen as a standard part of planetary adolescence, a necessary chaos that clears the way for life. The implications are staggering. If our architecture is common, then worlds like Earth are common. The specific conditions that allowed for a stable, billion-year incubation of life-liquid water, a stable orbit, plate tectonics, a protective magnetic field, a large moon to stabilize our tilt may not be a bizarrely specific checklist, but a reliable recipe. In this future, the galaxy is not just teeming with planets. It is teeming with Earths. It is a galaxy filled with potential. The silence of the cosmos, the Fermi paradox, where is everybody, would become an even more pressing and puzzling question. The answer would shift from because life is impossible to because life is fragile, or because intelligence is a fluke, or because civilizations do not last. The galaxy would be a garden of potential, and our task would be to find the other flowers in this future. The data reveals a stark truth. We are the exception. Jupiter twins around sun-like stars are found in 1 in 10,000 systems, or even rarer. The peas in a pod architecture is not just common, it is virtually the only game in town. Our solar system, with its clear separation, its mixed bag of worlds, its solitary giant standing guard, is a cosmic fossil, a relic of a bygone and unusual process. Finding these worlds was a painstaking process. It wasn't automatic. Astronomers had to first identify stars whose motion couldn't be explained by parallax and proper motion alone. They had to see that tiny additional wobble in the data. Then they had to rule out other causes, like the subtle tug of a faint stellar companion. Finally, they followed up with the old, reliable Doppler method to confirm the planetary nature and get a mass measurement. It was a cross-examination of the evidence, and the evidence was rock solid. Gaia 4b and Gaia 5b are definitely there. So, What do these first discoveries tell us? First and foremost, they are a proof of concept. They are Gaia's way of turning to the astronomical community and saying, "See, it works. I can see them." They proved that the mission has the precision to detect the gravitational tug of giant planets from thousands of light years away. Second, they are scientifically fascinating in their own right. A giant superjupiter orbiting a small, dim star was thought to be an extremely rare configuration. Our core accretion models of planet formation struggle to explain how such a small star could accumulate enough material to build such a massive planet. Their existence forces us to reconsider the rules. Perhaps these giants form more like stars do, from the direct gravitational collapse of a cloud fragment. But the most important takeaway from Gaia 4b and 5b is this: they are the outliers that prove the rule. Their wide orbits made them nearly invisible to other methods. They were hiding in plain sight in the blind spot of our other telescopes. And in astronomy, where you find one, you usually find many. These two planets are not freaks. They are the first members of a hidden population, are the signal that there is a whole unseen menagerie of distant, long-period giants lurking in the Gaia data. Jupiter-mass planets, Saturn-mass planets, ice giants all waiting for their moment to be discovered. Gaia 4b and 5 billion are the first whispers from the darkness, the first few pages of a catalog we haven't even opened yet. The spacecraft has finished its data collection. Its primary mission is complete. The raw observations are in. The wobbles of 1 billion stars have been recorded. The dance has been captured. We are standing on the precipice. A specific date is circled on calendars in astronomy departments across the globe. It's not a launch date, it's a release date. Sometime in December 2026, a team of scientists in Europe will execute a command, and a data torrent will be unleashed onto the world. This is Gaia's Data Release 4, and it will contain, for the first time, the full time series astrometric data, the raw story of the stellar wobbles. This is the moment the ghost hunters get their ultimate tool. This is the day the map of our galaxy is redrawn forever. To understand why Drive 4 is different, we have to understand what came before. Data releases 1 through 3 were revolutionary in their own right. They gave us the most precise catalog of stellar positions, distances, and motions ever compiled. They were the finished, breathtaking map. But they were, in a sense, a summary. They gave us the average position of a star, its average motion. They were like giving someone the biography of a dancer, but not the film of the performance. Dr. 4 is the film reel. This upcoming release will include the time series. This means we won't just get a star's starting point and ending point. We will get a point for every single one of Gaia's observations. We will have a detailed, time-stamped record of its path through the sky, with all its tiny deviations and wiggles intact. This is the raw material of the wobble. This is the data that contains the fingerprints of the planets. Furthermore, Dr. 4 will span approximately 5.5 years of observations. That's nearly twice the baseline of the data used for Drive 3. This is critical. For a planet with a long orbital period, a longer baseline of observation means we can see a larger arc of its stars wobble. We can fit a more precise model to it. We can find planets with orbits of 5, 10, even 15 years with high confidence. We are no longer limited to the quick, frantic dances of close-in worlds. We can now see the slow, stately waltz of the outer giants. This is the fundamental shift. We are moving from a snapshot to a movie. And in that movie, the hidden actors, the cold Jupiters, the distant Saturns will finally step into the light dot. So, what can we expect? How many new worlds will this reveal? We don't have to guess. We have astrophysicists whose job it is to run the simulations, to forecast the coming deluge. I spoke to the experts, the people who have done the math, Caleb Lammers and Josh Wynn. They recently published a study that modeled what Gaia should find, and their predictions are staggering, based on simulated data that mimics Gaia's incredible precision. They predict that data release for ML will lead to the detection of approximately 7,500 new exoplanets. Let me repeat that. 7,500. This single data release is predicted to more than double the number of confirmed exoplanets. Overnight, the current count stands at just over 5,000. Gaia DR4 could push us well past 12,000. Think about the scale of that. Every exoplanet discovery you've ever read about, from the first pulsar planets to the entire Kepler catalog, represents a monumental effort over 3 decades. Gaia will, in one fell swoop, eclipse all of it. But what kinds of planets will these be? This is the most crucial part. Lammers and Wynn's models indicate that the vast majority of these 7,500 new worlds will be precisely the ones we've been missing. Giant planets on wide orbits. This is the end of the blind spot. This is the census of the suburbs. Gaia Drive 4 will give us our first ever robust statistical sample of Jupiter analogs and their larger siblings, the superjupiters. We will finally be able to answer the question, is our Jupiter normal? Is it common for a sun-like star to have a giant planet in a stable, distant orbit? Or is it, as some fear, a 1 in 10,000 occurrence? The initial candidates from Drive 4 will be followed up with targeted Doppler observations. Ground-based telescopes will point at these wobbling stars, using the radial velocity method not to discover, but to confirm and to refine. They will measure the planet's mass more precisely and nail down its orbital parameters. This synergy is powerful. Astrometry finds the needle in the haystack, and radial velocity tells us exactly what the needle is made of. But wait, it gets even bigger. Drive 4 is not the end. It contains only about half of the total data Gaia collected. The full, complete dataset will be released in Data Release 5, scheduled for the early 2030s. This will include astrometric measurements spanning a breathtaking 10.5 years. The effect of this doubled timeline is not linear, it's exponential. Lammers and Wynn's prediction for Dr. 5 is almost difficult to comprehend. 120,000 planet detections, give or take a few thousand. Let that number settle in. 120,000. A 20-fold increase over the number of planets we know today. This would be, by an enormous margin, the largest single discovery of planets in human history. It would transform exoplanet science from the study of individual, interesting systems to a true, robust field of statistical astronomy. There are 2 main reasons for this explosion. Longer orbital periods. A 10.5-year baseline makes Gaia sensitive to planets with even longer orbits, perhaps out to 10 astronomical units or more. This captures an even wider range of the Jupiter-like parameter space. This would be a revolution of a different, more sobering kind. It would mean the grand tack was not a common occurrence, but a freak gravitational accident, perhaps triggered by a passing star in the early cluster that just happened to create the conditions for our existence in this future. Earth is not just another world. It is a sanctuary, a fortress of habitability in a galaxy that is otherwise largely hostile to complex life. The conditions here are not a common recipe. They are a 1 in billion lottery ticket. The silence of the cosmos is no longer a paradox. It is the expected outcome. We are not failing to find others because our technology is primitive. We are failing to find others because there are no others. This knowledge would bestow upon us a responsibility of almost unimaginable weight. It would mean that life, consciousness, and civilization are not cosmic imperatives, but precious, fragile, and incredibly rare gifts. This pale blue dot would not be one of many. It would be the one. The only one we know of, and possibly the only one for millions of light years in any direction. The question of solar system architecture is not an abstract astronomical curiosity. It is directly tied to the probability of life. Let's delve deeper into why these two futures paint such different pictures for biology in the universe. Life as we know it requires time, vast, uninterrupted stretches of geological time. It took nearly 4 billion years for single-celled life on Earth to evolve into the complex, multicellular organisms we see today. This requires a stable environment. A solar system with a Jupiter-like planet in a stable, circular orbit acts as a gravitational anchor. It helps to shepherd debris, preventing the inner system from being subjected to constant, sterilizing impacts. In a peas-in-a-pod system, with many worlds in close, resonant orbits, the gravitational interactions can be chaotic. These worlds may constantly perturb each other, driving extreme volcanic activity like Jupiter's moon, Io. But on a planetary scale, or causing wild swings in orbital eccentricity that make a stable climate impossible. The very order of these systems might be inimical to the long-term stability life requires. Gaia and Tess together will tell us not just if a world is in the habitable zone, but what kind of world it is. Is it a super-Earth? If so, it likely has a thick, hydrogen-rich atmosphere, creating a crushing pressure and a runaway greenhouse effect, more like Venus than Earth. Is it a planet around a red dwarf? If so, it is likely tidally locked, with a permanent dayside and nightside, and subject to violent stellar flares that could repeatedly strip its atmosphere. Finding a true Earth twin planet with a thin nitrogen atmosphere, liquid water, oceans, and plate tectonics orbiting a stable, G-type star like our Sun, and doing so within a system architecture that provides long-term stability. This is the gold standard. The prevalence of this specific combination is what Gaia will help us determine. Is it the galactic standard for habitability, or is it the ultimate cosmic luxury? The Fermi paradox asks, if the universe is so vast and old, why haven't we encountered other intelligent life? One proposed solution is the Great Filter, a stage in the evolution of life that is so improbable that it effectively prevents life from progressing to the point of interstellar communication or travel. This filter could be behind us, the origin of life itself, the evolution of complex cells, or, ahead of us, self-annihilation through technology. The Gaia data could reveal that the Great Filter is, in fact, planetary system architecture itself. The filter is not biological, but astronomical. The formation of a system capable of nurturing life for billions of years may be the universe's most effective bottleneck. If Future 2 is correct, the filter is behind us, and it was the formation of our specific, weird solar system. We are the ones who made it through. How will humanity react to this knowledge? The answer will not be confined to scientific papers. It will seep into our culture, our philosophy, our art, and our very sense of identity. The confirmation that we live in a common system within a galaxy brimming with similar potential would be a powerful catalyst for the next great age of exploration. It would galvanize the scientific and political will to build the next generation of telescopes, massive interstellar probes, even with the explicit goal of studying these other Earths. The question, "Are we alone?" would become, "Who is out there?" This knowledge could foster a sense of cosmic kinship. We would see ourselves as part of a vast galactic community of life, even if we haven't yet made contact. It would instill a powerful optimism about our future, framing humanity as a species on the verge of graduating from its cradle and joining a much larger conversation. The confirmation of our profound solitude would be a shock to our collective psyche, but not necessarily a negative one. It could trigger a spiritual and philosophical awakening, unlike any in human history. It would force a radical revaluation of what it means to be human. In this future, Earth is not a disposable rock. It is the only known biological heirloom in the cosmos. This knowledge could become the foundational argument for a new global ethic of planetary stewardship. The fight against climate change, biodiversity loss, and pollution would no longer be framed as merely saving our way of life, but as a sacred duty to protect the only known cradle of consciousness in the universe. We are not just the tenants of this world, we are its guardians. It would also place a profound weight on our survival. If we are the universe's one known chance to know itself, then our self-destruction would be a cosmic tragedy of unparalleled scale. Our survival and flourishing would become a matter of cosmic importance. Even after the Gaia data deluge, mysteries will remain. In many ways, it will simply hand us a new and even more fascinating set of questions. Gaia can tell us about the architecture, and TESS and JWST can tell us about a planet's atmosphere, but they cannot tell us if there is life there. Detecting biosignatures like the combined presence of oxygen and methane, or the spectral signature of chlorophyllus, the next great challenge. This will require even more powerful telescopes, ones that can directly image a pale blue dot around a nearby star and take its spectrum. The hunt for life will become more focused, but no less difficult. Even if we find a billion Earth-like planets, we will have no way of knowing if any have produced self-aware, intelligent life. The evolution of intelligence, the rise of technology, the development of culture, these are filters we know nothing about. Are we the first? Were there others that rose and fell? Is intelligence a predictable outcome of evolution or a bizarre fluke? Gaia cannot answer this. Our newfound knowledge of our cosmic context must inform our future. Do we, as a species, have a responsibility to ensure that life from Earth endures? Perhaps by becoming a multiplanetary species. If we are common, this is an adventure. If we are rare, it is an insurance policy for the only known life in the galaxy. This is no longer science fiction. It is a strategic imperative shaped by its fundamental knowledge. We are the first generation in the history of humanity to be presented with this choice. We are the ones who will no longer have to look at the night sky and wonder. We will know the data is coming. It is a wave of truth rushing toward us from a million miles away, collected by a silent machine that did its job perfectly. It will not ask for our permission. It will not care about our hopes or our fears. It will simply tell us how things are. This knowledge will forever define what it means to live in this particular system, around this particular star, on this particular pale blue dot. It will tell us if we are the universe's way of being ordinary or its way of being extraordinary. We stand at the threshold. Soon we will cross it, and when we do, we will finally understand our place in the cosmic ocean. We will know if we are a single, lonely ship or part of a vast and endless fleet. Thank you for watching Psychology of Sleep. Please like and subscribe for more interesting topics.